Let's do one example. Describe the distribution of the sample mean. The weights of penny minted after 1982 are approximately normally distributed, with mean 2.46 grams and standard deviation 0.02 grams. What is the probability that a penny minted after 1982 weighed at least 2.465 grams? What is the probability in a simple random sample of 10 penny minted after 1992, we obtain a sample mean of at least 2.465 grams. What is this probability when we select any sample of size 10? The mean of this sample is this value. We can express this question symbolically using this notation: probability that individual value and probability that a sample's mean. Then in both cases, they are asking greater than 2.465 and greater than 2.465 in both cases. But in part A, the problem is asking probability that any penny selected randomly weigh more than this quantity. But in the second case, the problem is asking what is the probability that a sample of size 10, the mean of this sample is greater than 2.465. These are the two questions that we need to solve in this problem. We need to be careful because the problem is asking for probability of at least 2.465. So we need to include the equal in both expressions. Then let's analyze the graph of this distribution. That is the distribution for individual pennies. The mean is 2.46 and the standard deviation is 0.02. But we are interested in the distribution of all samples mean. Sample mean when my sample size is 10. The center of the distribution will be the true parameter, 2.46. Here we have all samples stock in this number line, such that the mean of all of these samples stock here is exactly the mean of the population, is in the center. And the standard deviation of this distribution will be this standard deviation divided by a square root of n. In this case, n is 10, and the standard deviation for this distribution is smaller than this. Okay? All of these points, all points in that distribution are closer to 2.46. All measurement of all of these penny are more spread around 2.46. Then my first question, here we have all penny. Remember, this is individual values and this is the distribution for samples mean. Individual value, here we stock all penny such that the weight of all of this penny is exactly 2.45465. And in this region, we have all penny that weigh more than 2.465, and this area should be proportional to the probability. For that reason, we need to find the area to the right of 2.465 in this distribution. And in the second problem, we have in this point 2.465, we are going to stock all samples size 10, such that the mean of all of these samples is 2.465. And in this region, we have all samples size 10, such that the mean of all of these samples is greater than 2.465. That is my second question. How can we solve this using formulas and tables? Let's do it. X, individual values are normally distributed with mean 2.46 and standard deviation 0.02. And that is the question. What is the probability that we select one penny such that this penny weighs more than 2.465? Then let's find the proportion of all penny that weigh more than this. How can we do that? That is the proportion of all penny. That is the all penny that weigh more than 2.465 in my distribution. Remember, all tables work only with z-score. If I know that this point here is 2.465, to work with table, the first step is to know how many standard deviation is this value from the true parameter. This one is the true parameter. How many standard deviation? That is the z-score. Then the z-score for this is 2.4. How many standard deviation we have between this value and the center of the distribution? That is the z-score for this quantity. This C-score is 0.025. 2.465 is located 0.25 standard deviation to the right because the C-score is positive. We can use the table to solve this problem, but remember, in the table we need to find this C-score, positive C-score table. Then we need to find 0.02 in this column, and the second decimal could be found in this row. In the intersection of this column with this row, we can find this number in the table. But what does this number represent? That is a percentile, percentage below. Actually, is the percentage of all pennies that are stocked in this distribution below 2.465. That is this area. But the problem is asking for this other area, the area to the right. Remember, table, all numbers inside this table represent area to the left. Then, because the total area under this distribution is 1, the area to the right will be obtained subtracting this number from 1. And this value is 0.413. And we can conclude that the proportion of pennies that weigh more than 2.465 is 40%. 40% of all pennies of the United States weigh more than this. Then, that is equivalent to state the probability to select any penny in the United States that weigh more than 2.465 is 40%. Second question, if we select a sample size 10, then we need to use a different probability because the standard deviation of the distribution for all samples mean is smaller, and that is the distribution. Remember, the center of the distribution is the true parameter and the standard deviation is smaller. We want to know what is the probability in the distribution that one sample's mean is bigger than 2.465. To do that, we need to find the C-score of this value. But remember here, the C-score is the value minus the center divided by the standard deviation in this distribution, which is smaller. The C-score in this case will be 0.79. That is our problem. The probability that any sample of size 10 weight is bigger than this number is equivalent in the standard normal distribution is equivalent that the C-score is bigger than 0.79 because this value is located 0.79 standard deviation to the right of the parameter of the center. Then to solve this problem, we can use table. We need to find 0.7 in this column and 0.09, the second decimal, in this row. And in the intersection of this column and this row, we have this number. And what does this number represent? Again, all numbers here in this table will represent percentage below. And this percentage is probability to the left of 2.465. But the problem is asking for probability to the right of 2.465. Then we need to subtract this probability from 1, and this is 21% of all samples, size 10. When we compute the mean of all of these samples, the sample's mean will be smaller than 2.465. That is our conclusion. Let's finish with this graph. And in this graph, we are going to study different populations. The first population is uniform distributed. The second population has this shape, 2 modes, and in the center we have that shape. That is an exponential distribution, and this is a normal distribution. From all of this population, let's select sample of size 2, size 5, and size 30. And let's analyze how the distribution for all of these samples taken from each of these populations. In the first case, when my sample size is 2, we got this distribution. For all samples mean size 2. When we increase my sample size to 5, it's closer to a normal distribution. And when my sample size is 30, actually, the distribution for all samples taken from this population will be normal. Incredible, yeah? This pi is uniform, the distribution for all samples mean is normal. The same thing happened with the distribution. When my sample size is 2, the distribution of all sample mean is really strange. But when we increase the sample size, it becomes more mound-shaped, the distribution. And when my sample size is 30, definitely is normal. And you see, incredible also. Despite this population is like this, individual value, the distribution for samples bigger than 30 from this population becomes normal. Incredible. The same thing happened with the exponential distribution. My sample size 2 and the sample size is 5, and in this case is 30, is normal. And you see, if we have any distribution, could have this shape, or this shape. When I analyze the sampling distribution, when my sample size is bigger than 30, all of them will become normal. All distribution for samples mean are normal. It is the distribution for individual value. However, when my distribution is normal, doesn't matter what is the sample size, the distribution will be always normal. Normal, sample size 2, sample size 5, normal, sample size 30 is normal. In all cases will be normal. That is the conclusion in this slide. And then key points from the example 4. The mean of the sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of the samples mean is the standard deviation of the population divided by a square root of n, and this result, the mean of all samples mean is equal the mean of the population, and the standard deviation of all samples mean equal the standard deviation of the population divided by a square root of n. This result is always true regardless of the sample size. You see, in all of these cases, the mean is equivalent to the mean of the distribution. Doesn't matter what is the sample size. The mean is the same of the distribution. The mean of all of the distribution will be the parameter, regardless of the sample size. And the standard deviation will have the same result. Doesn't matter how is the shape and how is the sample size. However, the shape of the distribution of the samples mean becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. But when my sample size is greater than 30, the shape of the distribution will be normal. That is an important conclusion. If the distribution of the population is unknown or not normal, then the distribution of the samples mean is approximately normal, provided that the sample size is greater than or equal to 30. That is very important conclusion. And the central limit theorem is regardless of the shape of the underlying population, the sampling distribution for all x bar becomes approximately normal as the sample size n increases.